In this lesson, we're going to learn about intermolecular attractive forces and their effect on boiling. And it involves something called vapor pressure. So what is vapor pressure? Well, it is the pressure of a vapor, which is a gas, when it is in contact with its liquid or its solid form in a closed container. So you can see here we have a closed container. Here we have a substance in the liquid form. Here we have a substance, that same substance in the gas form. So this liquid, some of the particles have absorbed enough energy to evaporate into a gas phase. And the pressure that those particles exert on the walls of the container is what is called vapor pressure. Right, so the vapor pressure is what is exerting by the gas. So why do we care? Well, vapor pressure of a substance, along with the atmospheric pressure, so those two together, vapor pressure and atmospheric pressure, can alter the boiling point temperature of the substance. We always know that water can boil at 100 degrees Celsius, but we're going to see that that's only at a very specific atmospheric pressure. So we're going to go ahead and make some observations. I'm going to show you a video that I'm calling evaporation races. And in this video, an equal amount of ethanol, acetone, which is sometimes referred to as propanone, and water are going to be placed directly on the lab bench. And I want you to notice on the timer when each drop completely evaporates. So you can see here the ethanol, the acetone, and the water. The acetone disappeared right about at 17 seconds. So that's the one that evaporated first. Water doesn't look like it's changing at all. Ethanol has finally evaporated at the end of the video at 33 seconds. And we can see here that ethanol, 33 seconds, took longer to evaporate than acetone was the first one to evaporate, and the water never evaporated at all. So some time greater than, I suppose we can say 33 plus seconds. So questions to answer here: which liquid evaporated at the fastest rate? Well, that would be the one that took the least amount of time, so acetone. The liquid that evaporated at the slowest rate is water. We didn't even get to see it completely evaporate. So based on these observations, let's try to draw a picture of the amount of vapor molecules above their liquids as if they were contained in a closed container at the same temperature. So if propanone, otherwise known as acetone, this is the one that evaporated the fastest. So if this is the liquid, up here we'd have a lot of vapor molecules compared to water, which would have the fewest. So I'm going to go ahead and draw, since acetone is the fastest one to evaporate, I'm going to draw, I don't know, maybe about 20 or so particles above. Didn't actually count those, but let's say we've got a lot of particles because it evaporates very easily. Ethanol was somewhere in the middle, so I'm going to draw maybe about half the number of particles. And then for water, I'm just going to draw a few. Okay, so based on the observations, which liquid is going to have the highest vapor pressure? Well, that's going to be acetone, the one that evaporated the easiest, the one that produced the most gas particles in the shortest amount of time. So proposing a possible explanation for how intermolecular attractive forces can cause differences in evaporation rates in the three liquids above, well, it must be that if acetone evaporates really easily, it must be that these particles are not attracted to each other very much in the liquid state. So we could likely assume that weaker intermolecular attractive forces is going to translate to a faster evaporation. And maybe saying the same thing, but just in the opposite direction, stronger intermolecular attractive forces is going to result in a slower evaporation. All right, so taking a look at the second page in your handout, let's see how vapor pressure is graphically related to temperature. So this is reference table H in the chemistry reference tables. It is called the vapor pressure of 4 liquids. We have 4 liquids here: propanone, which is acetone; ethanol, which is an alcohol that is based on the fermentation of corn or other starches, other grains; water; and then there's something called ethanoic acid, which is another name for acetic acid, which can be found in vinegar. So we have 4 liquids here. What do we have here on the x-axis? Well, on the x-axis, the independent variable here is temperature in degrees Celsius. And I want you to take a close look at the intervals. What is the intervals for how many degrees Celsius is each one of these intervals? Right? So if this is 25 and this is 50 and there's 5 intervals in between, then each interval is equal to 5 degrees Celsius. On the y-axis, we have vapor pressure in kilopascals. Right, we've got vapor pressure. So that's the dependent variable, is vapor pressure. And the unit it's being measured in is kilopascals. And each interval on the y-axis is not 5. If this is 0 and this is 50 and there's 5 intervals in between, then each one of these little intervals is equal to 10 kPa. So this is something that's easily confused. Remember, you got 5-degree intervals here and intervals of 10 kilopascals here. So a couple more questions here. What kind of relationship exists between these two variables? Well, you can see all of these graphs go up and to the right. So this would be best classified as a direct relationship, which means so as temperature increases, then vapor pressure also goes up. Now, there's a dashed line at 101.3. That 101.3 is what we call standard pressure. And if we know our equivalencies, standard pressure is also the same thing as 1 atmospheres or 760 millimeters of mercury. So the dashed line at 101.3 kilopascal helps you locate standard pressure. Okay, a couple questions. Notice there are 4 liquids, 3 of which we just saw in the evaporation races video. Right? The ones we just saw were acetone, ethanol, and water. Consider the 4 liquids at 60 degrees Celsius. List the 4 liquids in order of increasing vapor pressure. So at 60 degrees Celsius, let's find that. This is 50, 55, 60. And as we go up with increasing vapor pressure, the first liquid is acetic acid. The second liquid is water. After water, we have ethanol, and after ethanol, we have acetone. Which of these liquids at 60 degrees has the weakest intermolecular attractive forces? Remember, weakest intermolecular attractive forces are going to have the highest vapor pressure. So at 60 degrees, the highest vapor pressure is going to be propanone. So that's how you can read those. Okay, let's go ahead and turn to the third page of the notes. So let's see a demonstration to show us the impact that atmospheric pressure has on the boiling temperature of water. We know that the normal boiling point of water is 100 degrees Celsius. Let's see what we can do about the boiling point of water in a vacuum chamber. So I'm going to pause the video right here, and I'm going to show you a video of this demonstration. All right, so I've got the sound down, but we've got a beaker of water with a measured temperature of about 20.8 degrees Celsius. This is essentially room temperature water. You can't hear the sound. I do have it turned off, but the vacuum pump is being turned on. So we are reducing the atmospheric pressure. The water is at about 21 degrees Celsius, so it's exerting a certain vapor pressure. And as we reduce the atmospheric pressure, we can see that bubbles are starting to form, and bubbles are starting to rise. And it appears that the water is boiling, but the temperature is still only 20.8 degrees Celsius. And the bubbles are forming more rapidly now. And we can see the temperature is still 20.8 degrees Celsius. And now the water is boiling very vigorously. So what is going on? This water is not being heated. The only thing that we are doing is we are reducing the atmospheric pressure. And it's still maybe a little bit colder there. So we can see that the boiling point of the water was about, we're going to round it to about 21 degrees Celsius. So this leads us to believe that a liquid's boiling point, and I'm going to abbreviate that, the boiling point temperature, right? Normally we know it's 100 degrees, but we were able to make the water boil at only 21 degrees Celsius. So we somehow see that a liquid's boiling point temperature depends on atmospheric pressure. So let's see another demonstration to show us the impact that vapor pressure has on the timing of vaporization of 3 liquids. This is actually going to be 2 liquids, this demonstration. And what we are going to do now is I will show you a video of acetone in a beaker compared to water in a beaker. And we know that these have different vapor pressures because we just saw their graphs on reference table H. They have definitely have different vapor pressures over many different temperatures. Let's see what happens when we put them into a vacuum chamber. Okay, so I'm going to show you this video sped up a little bit at 1.5 speed. All right, so here's the video that has both water and acetone in the vacuum chamber. And we are reducing the atmospheric pressure. And we are going to see here, I do think I have this sped up a little bit. Maybe let's see. No, let's speed it up a little bit. Okay. So as I am starting up the vacuum, you can see that the acetone has boiled almost immediately, but the water is just starting to show signs of boiling. So acetone is vigorously boiling. It must have a boiling point temperature much lower, must boil much easier, and water was just starting to boil. So here we can see that acetone boiled first and water boiled second. So this leads us to believe that a liquid's boiling point temperature also depends on vapor pressure. And based on what we've seen here is that a liquid's boiling point depends on both atmospheric pressure, I didn't leave very much room, did I? Atmospheric pressure and vapor pressure. But how? All right, so what we need to see is that a couple things to understand this is that vaporization definition is a phase change from liquid turning into a gas. It includes both evaporation and boiling. So it's sort of a generalized term. Vaporization is any change from liquid to gas. So what's the difference between evaporation and boiling? Well, evaporation is when the phase change is only happening on the surface of liquids at all temperatures. It is related to the intermolecular attractive force strength. Weak intermolecular attractive forces will result in a fast rate of evaporation, whereas a strong intermolecular attractive force will result in a slow rate of evaporation. But evaporation only happens from the surface. Boiling, on the other hand, is when the phase change happens throughout the liquid. So here we can see that the phase change is not just happening at the surface, but these little bubbles are not air, it's actually water molecules being turned from a liquid into a gas, and then that gas bubbles float up to the top where they are released. So boiling is the phase change as it happens throughout. Evaporation is the phase change where it happens only at the surface. Okay, so let's take a look at putting this all together. Key points. The strength of the intermolecular attractive force determines how readily a substance will evaporate from the surface of its liquid, which in turn will impact how much vapor pressure it can exert. The stronger the intermolecular attractive force, the slower it will evaporate. The weaker the intermolecular attractive force, the faster it will evaporate. Strong intermolecular attractive forces will result in the substance having a low vapor pressure, because if it's strong, the substance is not going to vaporize very readily, so there will be very few vapor particles and therefore a low pressure. Whereas weak intermolecular attractive forces will result in the substance having a high vapor pressure. Key point number 2, temperature and vapor pressure of a liquid are directly related. As the temperature increases, the molecules will have a sufficient kinetic energy, which I'm going to abbreviate as KE, to escape the intermolecular attractive forces between the liquid molecules to be able to change phase and turn into a gas or gaseous molecule. The more particles in the gas phase or vapor, or in the vapor phase, the more pressure, vapor pressure, they can exert. Conversely, as temperature decreases, molecules will slow down, and when the gas molecules come close enough to the surface of the liquid, their intermolecular attractive forces will capture the gas molecules and cause them to turn into the liquid state. The fewer particles in the gas phase, the less pressure they can exert. Okay? So increased temperature, increased vapor pressure. Decreased temperature, decreased vapor pressure. The direct relationship. Key point number 3. Boiling point is a temperature when gas bubbles form throughout the liquid. This only happens when vapor pressure is equal to atmospheric pressure. Right, so VP is vapor pressure. When vapor pressure is equal to atmospheric pressure, then boiling can happen. So you can make that happen one of two ways. You can increase the vapor pressure by heating up the liquid. When you heat up the liquid, you increase the vapor pressure until it equals atmospheric pressure. This is what you typically think of as boiling. Heat up the liquid, it boils. But the other thing you can do is you can, if you have a cold liquid with a low vapor pressure, you can lower the atmospheric pressure, which is what we did in the vacuum chamber. So if you lower the atmospheric pressure to match the vapor pressure being exerted by the liquid, then you can also make it boil. So there's two ways to make it boil, and you can manipulate either the vapor pressure or the atmospheric pressure. Okay? So when vapor pressure is less than atmospheric pressure, the gas particles within the liquid do not have enough kinetic energy to break free from the intermolecular attractive forces under the surface of the liquid. So typically, we will heat the liquid in order to increase the kinetic energy enough so that vapor pressure becomes equal to atmospheric pressure. And when vapor pressure equals atmospheric pressure, we see bubbles form throughout the liquid. The temperature this happens at is called the boiling point. So let's go back to the graph that we made, or that we were looking at. And let's look at the water graph. Okay. Normally, water will boil, this is the water graph right here, at 100 degrees. That's the normal boiling point of water. Okay. But that is what we call the normal boiling point, because that's when the atmospheric pressure is at standard pressure. So in order for the vapor pressure to match atmospheric pressure, you have to heat it up quite a bit. So water will, when the pressure of the liquid is at 101.3, and that equals atmospheric pressure, then the water temperature has to be at 100. But when we saw the video, that water was only at about 21 degrees. So if we look at that, okay, water's vapor pressure at 21 degrees, right, is only about, what is it, 10, 20, call it about 25 kPa. Is that right? 25 kPa. Okay. So water is exerting a vapor pressure of only about 25 kilopascals when the water temperature is about 21 degrees Celsius. That's not normally the temperature it needs to boil. But when we brought the atmospheric pressure in the vacuum chamber down to about 25 kPa, then that water could start boiling. So this graph, you are able to read boiling points, the temperature, or you can figure out at any pressure, right? At any pressure, you can figure out what temperature that liquid will boil at. So at 150 kilopascals, acetone will boil at about 68 degrees Celsius. Okay, so any point on any one of these four graphs will tell you, let's write this, make sure this is on the screen. Any point gives you the boiling point of the liquid at the specified vapor pressure and temperature. So boiling point temperature will tell you, or any point on the graph will tell you the boiling point of the liquid if the vapor pressure is that pressure and the temperature is that temperature. So in this video lesson, we have taken a closer look at how vapor pressure is dependent on intermolecular attractive forces and how that vapor pressure determines the temperature that a liquid will boil at. That's it for this video lesson. We'll see you back in the classroom.